Lesson 26, Energy, Work, and Power. Okay, so if we kind of go back what we've covered so far in this course, we've done kinematics, which was a really successful way of describing how things move. We've talked about dynamics and Newton's laws, which has also been really good for describing why things move. And it was actually a really powerful theory at the time. And it had so much success that like people were trying to apply it to everything. They were trying to apply it to things like, how gases behave and those type of things. But it turned out there was actually something else that was needed and was a lot easier. Was something it was the idea of energy. And energy is kind of a strange concept, as much as it seems kind of intuitive, like what we mean by energy. Um, it's kind of weird. So if you think about what energy is, you've probably talked about these things in earlier years, or I know you guys have in Science 10. Energy can exist in chemical form. It could be radiant energy. We're talking about like light or X-rays or any of that kind of stuff. Electromagnetic, so it could be like battery or current in a wire from electricity, or atomic. We are going to be dealing mostly with mechanical forms of energy. So, mechanical forms of energy, you should have seen this formula last year in Science 10. EK is equal to 1 half mv squared. And this one, EP is equal to mgh. You probably haven't seen this one yet. It looks a lot like that one, but it's going to be for a spring. So those are going to be our energies, or our formulas that we're going to be using here in a minute. So in Physics 30, we're going to be talking about radiant energy, electromagnetic, and atomic energy. But for this course, we're going to be talking mostly about mechanical energy. Like I was saying before, there are two types of mechanical energy, kinetic and potential. Go ahead and read through this on your own, but I'm going to move past that. So there are two laws of energy. So the first law of energy is, maybe you've heard this one before, that energy can't be created or destroyed. It can only change forms. That's generally how you would sum up what this says here. The second law of energy is about how you can't have a perfect system. So heat will always be lost. That's kind of an easy way to kind of sum this one up. That no matter what kind of device you have, so let's say you've got like a machine that you've created that does something, heat will always be lost in that process. So when you convert from one form of energy to another, heat's always a byproduct. And it gets a little bit more complicated than that, but for our purposes, that'll be good. Okay, so work. That's the first of the three big concepts here, right? So work, just to give you guys a bit of an idea here, let's pretend that you had somebody, sitting here, and they were doing a wall sit. Have you guys ever done a wall sit where your back's pushed up against the wall? And let's say they stayed there for an hour. You might say, well, man, that's a lot of work. But actually, when we're talking about in scientific terms, there's no work done there. Work is equal to force times distance. We're going to talk about that in a minute. So there was a force here. There was definitely this person applying a force to be able to do the wall sit, but the distance that this person traveled was 0. So this would be force of something times 0. The work done there is 0. Even though, so we have to kind of get our head wrapped around talking about work different than we talk about it in everyday life. You might also say that, man, I did a lot of work on physics last night, like dragging that pen across the paper. That wouldn't actually be that much work, right? But like physically, but mentally, the way we talk about work in everyday life, yeah, it would be. Okay, so number 1 here, ways to think about work. The primary definition of is work is done on an object if its mechanical energy, kinetic, or potential energy changes. This is a big one. This is one that seems like everybody forgets. Work is equal to a change in energy. So say that with me. Work is equal to a change in energy. It's going to be important. So let's say that I have something like a car, and it's going this way, and it's moving at 5 meters per second. And then it speeds up to 7 meters per second. work was done. There was a change in energy. This thing had a certain amount of kinetic energy. We'll talk about how to figure out what that energy would be from 5 meters per second. But then it went up, right? It had a certain amount of kinetic energy, then it had more kinetic energy. So work was done. Same thing if, let's say I lifted something. So over here, let's say I've got, some object that is 10 meters off the ground. Let's say that I lifted it up another 2 meters. So now it's 12 meters off the ground. There was work done on that object because it had a certain amount of potential energy. I gave it more potential energy. I changed its energy. So the change in energy is equal to work. And then the second concept of work is going to be work is equal to a force times a change in distance. So that's kind of what I was talking about when I had the person doing the wall sit. Yeah, so, but I'll give you another idea here though. So let's say that you are holding a book and you are applying a force upward, right? Force of gravity is pulling down. And the force that you're pushing up is equal to that, right? And let's say you're walking with that book. So now you're walking in this direction. This doesn't really count. Like I can't just go, well, FA is equal to, work is equal to FA times the distance that I walked, because FA and the distance are in different directions. So this formula only works for this in the same direction. So what I mean by that, let's say you had the situation like I have down here where you're pulling a box on an angle, right? And there's a certain distance that you went over. I can't just take this force, multiply it by this distance and say that's how much work was done. What you need to do is figure out what the x component of my force is. So what I really need is Fx, the x component of F, right? So I have to start breaking these things into our components again. So our formula can be now work is equal to force times cosine theta times d. And that's because f of x, if you were going to figure out what that would be force times cosine theta. So force times cosine theta times d, that's what work would be. Work is going to be a scalar quantity, so that means we won't have to worry about our directions when we're doing that, just the magnitude, so that'll be a little bit easier. So let's say, just before I carry on, let's say that I move this force that I was applying straight up and down. So now it was 90 degrees, right? Well, then no work would be done. If you put in force times cos 90 times distance, you would get 0. Cosine of 90 degrees is equal to 0. Because they have to be in the same direction, right? All right. And work, I kind of missed this, is going to be equal to newtons times meters or joules. I mean the same thing. I'll let you guys look through number 1 on your own there. I think it's pretty straightforward. And I'll let you guys look through example 2 as well. So, okay, next concept here is going to be network. Not like the internet, like having a network, but like net overall work. Okay, so work, like we said, was defined as change in energy. So work, though, what we're going to be able to start doing is calling it negative or positive. And I think example 3 is going to make that a little bit clearer. So a weightlifter is bench pressing a barbell whose mass is 110 kilograms. He raises the barbell a distance of 0.65 meters above his chest and lowers the barbell the same distance. The weight is raised and lowered at a constant velocity. Determine the work done on the barbell by the lifter when A, the barbell is lifted, and B, when when it's lowered. What was the net work done? Okay, so things we know: mass, we know change in distance, and we want to know what the work is. So one thing to note though is that since it was moving at a constant speed, F net's going to be equal to 0. So we can say the force up is going to be equal to the force of gravity. So it's going to be equal to mg. So part A is going to be pretty straightforward. We just need to go work is equal to force times distance. And knowing that force is going to be equal to mg, we've just replaced force with mg there. And that's equal to 110 times 9.81 times our distance. And we'd say that's positive, that, right? So now we can say on the way back down, though, it's going to be, everything's going to be the same, but we're going to be going down 0.65 meters. So it's going to be negative 0.65 meters. So the work done on the way down is going to be negative 7.0 times 10 to the 2 Newton meters. So the net work, the work up and the work down, is going to be positive and then minus the same thing. The net work here is going to be 0. So what we have to get straight is that it depends what we're talking about. So if you consider just lifting it up, then we're going to have positive work, right? If you consider just letting it down, we're going to have negative work. But if you consider both of them together, our change in energy would be 0. Because we went from having a certain amount of energy and then we're back at that same amount of energy. So what we're going to have to consider, though, after this is if we have something like a frictional force, we're going to have to take that force into account too, and the work that's being, done to hold that object back or something like that. So I'll show you an example of that right here. So example 4, a 50 kilogram crate is being dragged across the floor by a force of 200 newtons at an angle of 40 degrees from the horizontal. The crate is dragged a distance of 5 meters and the frictional force is 60 newtons. So if you drew your picture out like this, part A says, what is the work done on the crate by the applied force? So what we're looking for is the x component of the force. And we find that x component of the force by just multiplying by cosine theta. So to do that, we would end up having force times cosine theta times distance, or distance times cos theta. And you get 766 newtons times meters, or joules, same thing, right? Now it says, what is the force done on the crate by the friction force? So that one's just, well, the friction force is 60 newtons. And it's going to be over 5 meters, right? So that's going to be 300 newtons times meters. And we're going to say that's to the left right now. So what is the net work done here? Well, that's just going to be the two works subtracting each other. So we've got 766 minus 300, and the net work done on this object is going to be 466 newtons times meters. So part D, what forms of energy were produced by the net force and the applied force? The net force would be just kinetic energy. So if you think about like the overall force, we had some force going that way and then some going back. It's the net force that we're going to say was responsible for all of that kinetic energy going forward. The applied force, though, that's going to be this one. Well, that's going to be responsible also for some of the heat that's going to be lost, right? And that's going to be lost in the form of friction. So that's from the frictional force. Hopefully that wasn't too confusing. But also looking at this, we can say that the net force is what causes a change in kinetic or potential energy of an object. Okay, so the work energy theorem now. So the definition of the work energy theorem is that work results in a change in mechanical energy. What we're going to be able to do is figure out formulas for kinetic energy. And I'm going to let you guys look through this on your own just for the sake of time to see how how these were rearranged. And then gravitational potential energy, that's our next new formula. And then elastic potential energy, that's our last one. So yeah, take a look at those. If we look through some of these examples, I'm going to let you look through example 5. I'll do example 6 here, or I'll explain it. It says, an archer draws an arrow back by exerting an average force of 90 newtons on the string. If the string is drawn back 80 centimeters, what is the elastic potential energy of the bowstring? Okay, so we know force is 90, distance is 0.8. When you want to know potential energy. So potential energy is going to be equal to the work done on the bow. And here's the tough bit that people seem to always forget. So this is our bow. Work was done to pull that bowstring back to here, right? There was a change in energy. It had, well, no potential energy to begin with, and then it gave it some potential energy by bringing it back. That change in potential energy, change in EP, that's equal to work. So that's kind of step number one, is recognizing that a change in energy is work. Now that I know that work is equal to force times distance. And that works out quite nicely because I have a force and I have a distance. So the potential energy that's going to be here is going to be the work done on the bow, which is 72 joules. All right, looking at example 7, it says a 50 Newton force stretches a spring by 0.75 meters. What's the spring constant and how much energy is stored in the spring? So the first part's from last lesson. We have force, we have a distance. We just need to rearrange this equation to get it to look like that, and then figure out that our spring constant is 66.7. Now that we know that, it wants to know how much energy is stored in the spring, we need to use our potential energy for a spring equation. So that's 1/2 k x squared, where k stands for the spring constant, x stands for your displacement. And you get 18.75 joules. Our sig digs aren't right, though. Sorry about that. What is the kinetic energy of a 40 kilogram object that is traveling at 50 meters per second? So this one, need to use our kinetic energy one. Speed is kinetic energy, right? So that's going to be 1/2 40 times 50 meters per second squared. That's 50 joules. All right, so most of this stuff, other than this formula, these are all things that you guys did in grade 10 science. All right, power. Kind of throwing a lot at you guys. You'll be all right, though. So power is the rate at which work is done. So how fast is energy changing? I guess you can say it that way too, right? So power is going to be equal to work over time. So when somebody says, man, that's a really powerful car, you're saying that it's able to do a lot of work or change its energy over or a lot of energy over a certain amount of time, which kind of makes sense too, right? Because if you had a car that was able to go from like 5 meters per second up to 60 meters per second in like 1 or like 2 seconds or something like that, that would be a lot of power. That's a big change in energy over time. Okay, just so you guys are aware where these are. So here it is, right? Power is equal to change in energy over time, or work over time. And then there's some of the other ones that we've been doing right now too. All right, another useful alternative or alternate formula, which is not in your formula sheet, but if you want to memorize it or remember how we got it, go for it. So if you start off with power is equal to work over time, and then replaced work with force times distance, because that's what work is equal to, then I can also look at this and say, well, this is the same as force times velocity, because velocity is equal to distance over time. So P is equal to force times velocity. All right, so example 11, how much work can a 1.5 kilowatt kettle do in 10 minutes? So I want to change it into watts, or standard unit. Change time into seconds, and then just plug it in. So power was equal to work over time, so work is equal to power times time, and that's going to be 0.9 megajoules. Okay, example 12. A car driven at 100 kilometers an hour is overcoming a frictional force of 3,200 newtons. How much power is being produced? What is the horsepower? So here is where this formula P is equal to force times velocity is going to come in handy. So we know that the force is going to be 3,200 newtons because, well, it's traveling at constant velocity too, right? So it's going to be equal to that friction force, the force holding it back. V is going to be in meters per second. If we just divide by 3.6, that's 27.8. So now power is equal to 88.9 kilowatts. And then you're not expected to remember that 1 horsepower is equal to that. But if you did, that's how you'd figure out how many horsepower there was. Okay, so I'm going to end that video there, and I'll pick up with the practice problems in the next video.